in this session we are going to talk about isolation levels. There are three items that we're going to cover. The first, we're going to talk about some bad data issues, things that might go wrong when you're reading data. The second thing we're going to talk about is isolation levels and how those isolation levels can resolve or at least make you aware of the types of bad data issues that you might receive when you're running a query. And we're going to conclude by talking about deadlocks, what they are, how you can recognize when one's occurred, and what you can do to resolve it. First, let's talk about bad data issues. And the first one we're going to talk about is a dirty read. And this bad data issue, I think, is best understood by looking at an example. Here we're going to imagine for a second that we have a table with pricing data in it for our products. And we're showing the prices. We're showing the prices here. We're going to run a query that looks at that's going to retrieve all the prices for all of our products. So as our query starts, it reads through and it starts to get prices out of the table, and it reaches this point. And at this point, someone in another session starts a transaction to change the price of this product here from $30 to $33. Our query continues to run, picks up the new data, and then another transaction happens that modifies data. And this one is going to modify the price for this product here, the $40 price, such that it moves the product to an earlier spot in the table. Likewise, a similar modification takes the $15 product and moves it to a spot later in the table. Now, it doesn't change the prices. It's just the modification had the result of moving the location where that price was stored in the table. Our query continues to run, getting the $35 price for this product, and then picking up the $15 price, and then picking up the $45 price. And this is the result that's returned to us. As you can see, there are several problems with the result that we got back. First, the $40 price that was in the table isn't reflected in our result anywhere. It's a valid price for a product, but it doesn't show up in our results. It was missed. This $33 price here was part of a transaction that wasn't committed yet. It's very possible that the connection in the session that modified this price, that had the transaction open, may roll it back, in which case we have a price now in our result set that never really should have existed. In addition, we received the $15 price in our result set twice. That's because it was moved from an earlier spot to a later spot while our query was running, and we picked it up 2 times. These 3 types of issues are called dirty reads. These are the things that can happen. You can read data that was never committed, and that's the one that people usually think of when they think of a dirty read, is data that didn't actually exist. But likewise, we could miss data or read data twice. These 3 types of issues are called a dirty read. Other types of bad data issues are a non-repeatable read. A non-repeatable read occurs when you start a transaction and you run a query that selects data out of the database or accesses data. And later in the transaction, you run the same query again. And you either notice that on the second query that there are rows that are now missing, that are no longer there, or rows that were there before, but values on that row have changed and modified. That's a non-repeatable read. You repeat the query, but the data that you get wasn't repeated. It's been changed. The third type of bad data issue that we're going to talk about is called a phantom read. This is similar to a non-repeatable read in that you begin a transaction and you access data, and later in your transaction you access data again. The second time, though, instead of having missing or changed values, you actually have new rows that are added in that didn't exist before. Okay. So the 3 types of bad data issues that we've discussed are dirty reads, non-repeatable reads, and phantom reads. Okay, now we're going to talk a little bit about isolation levels and how the different isolation levels that are available in SQL Server help to resolve bad data issues. And where they don't resolve it, educate you about the types of bad data issues that you might encounter. The first isolation level that we're going to talk about is read uncommitted. Now, you may have heard of no-lock. No-lock is a query hint that you can add to a query, and essentially what it does is it enables read uncommitted isolation for the read uncommitted isolation level for the data access for your query. Now, read uncommitted allows all of the bad data issues. Not only does it allow you to have phantom reads and non-repeatable reads, but it also allows you to get dirty reads. Now, you may ask, how is this possible? Thought that locking took care of making sure that we didn't have any bad data, any dirty reads. Well, the answer is very easily shown in the lock compatibility matrix. You may have seen this before, and it shows, for example, if there is an exclusive lock on an object, let's take, for example, a row, and another connection requests a shared lock on the same object, that second lock, the shared lock, won't be granted because there's an exclusive lock that already has access to that row. This is similar to the situation that we just saw in our example where we had a row where the product price was $30 and it was updated to $33. Okay, the transaction that did the update had an exclusive lock on that row. Our query, when it came down to read that row, may have asked for a shared lock, and if it had, that lock would have been denied and our query would have waited for the exclusive lock to be resolved. However, the difference is that in read uncommitted, no shared locks are requested. So if we had been working in read uncommitted isolation, then we would have asked for a shared lock. Because we didn't ask for a shared lock, this compatibility matrix doesn't come into play because we weren't asking for a lock. So there would have been no conflict and we were able to read the data even though there was an exclusive lock on the row. That's how we get our dirty read. It's not that read uncommitted and no lock don't honor exclusive locks, it's that they don't ask for shared locks. That's an important thing to realize with the isolation levels. What the isolation level changes is the type of locks that you, in your session, request and how long those locks are held. In the case of read uncommitted, it doesn't request shared locks when it's accessing data. So it flows along very easily with data updates because the read uncommitted isn't going to ask for a shared lock and be blocked by an update. Now, conversely, and also similarly, you remember in our example that we had a row that had a price of $15. And after we had read past that row, another connection came and updated that row, and the update caused that $15 price to move to a different spot in the table where we read it twice. If we had asked for a shared lock on that row, when the other connection asked for an exclusive lock, it would have been denied and it would have had to wait for our select to finish. However, again, since in read uncommitted we didn't ask for any shared locks, we didn't have the $15 row locked. So when the other connection came along and asked for an exclusive lock on the row, it was granted. And it was able to make the update. And that's why we ended up reading it twice. Now, interestingly enough, here's another piece you need to realize is that all of the isolation levels do set locks. Even though read uncommitted and the word no lock are often used synonymously, it does set locks. And the locks that it sets are going to be on data modifications. All of the isolation levels need an exclusive lock in order to make a data modification. So even if we're using read uncommitted or no lock and we want to delete a row or we want to update a row, we will need an exclusive lock. Because we're going to get an exclusive lock, other modifications may be blocked behind us. Likewise, if there's already an exclusive lock on a row that we want to change, even if we're in the read uncommitted isolation level, our exclusive lock will still be blocked until the other update either completes or rolls back. In addition, read uncommitted will set locks at higher level objects, such as the table and the database, to make sure that the table isn't changed or dropped during our read. So we will get the shared locks at those higher levels, which can block data definition language or DDL actions if another connection is trying to modify the table in some way. So it does still set locks, but what it doesn't ask for is the shared locks. You can see how this has the impact of making it so that a lot more queries are able to run, because we don't have blocking when a writer wants to read something that a no lock or a read uncommitted transaction is reading. A writer isn't blocked. Likewise, if a writer has a row already locked, our read uncommitted reader isn't blocked behind it as well. Okay, now I have a friend of mine who's a respected consultant and a national speaker made this comment about no lock. He said, when is it appropriate to use no lock? And the answer that he gave was never. Now, I think there are probably places where you can use no lock appropriately, but it's in places where you don't care about the data. If you're storing data in the database, it seems like you probably do care about it. I mean, when would you want to insert a row or update a row but not care if you ever read the correct data back out or not? The only case that I can think of would be when you're aggregating a very large amount of data and being off by just a little bit doesn't make much difference to you. But for the most part, if you have data in the database, you want to get it out, and you want to get it out exactly as you put it in. Otherwise, you wouldn't have stored it there in the first place. So I agree with Randy, and I think that the use for no lock and read uncommitted is probably very seldom, very rare that we would see that. Okay, the second isolation level that we're going to talk about is read committed. This is the default for SQL Server. The read committed isolation level is the isolation level that most of your transactions will run under. It prevents dirty reads, and it gets shared locks for the duration of the statement. This means that if you have a transaction with multiple statements in it, the shared locks are only held while each individual statement is executed, then they're released. If someone wants to modify the row, but you're still in the transaction, that's okay, they can do that, as long as that data access isn't happening at the exact time. And if you change data inside of a read committed transaction, then your exclusive locks are held for the duration of the transaction, even though your read locks are not. And this is a common misconception. This is one that I had for quite a long time, is that under read committed, that those shared locks really only last while the select statement is running. Or, excuse me, it's not necessarily a select statement, so let me correct that. The shared locks are held for the duration of the data access, and then those shared locks are released. So this means that if you have a query at the beginning of your transaction, it will create shared locks on the data that you're accessing. If you then have another query late in your transaction, the original shared locks have been released and data could have been modified in between, and that second data access may see a different set of data than you had in the first one. And you remember from our previous slide that that is a non-repeatable read. Those non-repeatable reads are prevented at the repeatable read isolation level, which is the next one here on our list. With repeatable read, the read locks or the shared locks are held for the duration of the transaction. So updates and deletes from other sessions are prevented because they would request an exclusive lock but have to wait because your shared locks are still open. With repeatable read, once you execute a select, those rows are locked and they stay that way until either commit or roll back. However, because you're locking specific elements, either a specific row or specific pages, then you are not blocking inserts that might happen as well. That insert may be something that when you query again, you then get new data you didn't have before. That would require a range lock, or locking not just specific objects, but a domain or a range. And that is what the serializable isolation level gives us. It will lock a series of, not necessarily rows, but it will lock a range that, and then an insert that tries to insert into that range would be blocked because the range is actually held as well. And so serializable is where we are able to block phantom reads. Now over here on the side of the slide, I have two arrows. The arrow pointing up here is pointing towards more concurrency. As you move up these isolation levels from serializable all the way up through read and committed, you gain more concurrency. That means that more queries are able to run in parallel. Particularly here, we're thinking of data modification and data read concurrency. So serializable prevents a lot of concurrency because you're holding not just locks on objects, but locks on a range, and you're holding them for the entire transaction. So concurrency is very low with serializable. Read uncommitted, no shared locks are even taken. So there's a lot of concurrency there. The other arrow here pointing down shows that as we go down, we have increased contention, which is really kind of the opposite of the concurrency arrow. As we have less concurrency, we have more contention, more connections trying to access the same data and having to work around the locks that are there. So the isolation level that you pick depends on the type of bad data that you're willing to put up with and how much concurrency you absolutely have to have. Now, something new and very interesting that was introduced in SQL Server 2005 is an isolation level called snapshot. Now, snapshot isolation takes advantage of row versioning. Essentially what happens is that every row is tagged with a version, and when a data modification is made, like an insert, an update, or delete, the old data is stored in tempdb and the new data is given a new version number. So let's look at this graphical example here. Here we have a table in our production database, and with names, and then here on the side next to the name, I have made up a version number. In reality, the numbers are a lot bigger, but for the purpose of this example, I wanted to keep them short so we could very easily compare and see the version for each row. Okay, if someone wanted to update Brad's name from Brad Pitt to Brad Burr, the row would be updated, and a version of the old data would be stored in TempDB. Row versioning keeps the old copies of data modifications around until SQL Server determines that they're not needed anymore. Now let's see how a select statement can take advantage of this row versioning. In this example, we've already updated Brad's name, and the row version was created with an ID ending in 100 as our new version, and the old version with an ID of 50 is stored in our TempDB. Okay, so we've updated Brad and we've committed it. Okay, in the next step, let's say that someone didn't update to fix a spelling error in Mui's name. The transaction was started, and the new data was given an ID, but the transaction was not committed yet. Okay, then we have a query that begins in snapshot isolation mode, and it begins to select from our production table. Okay, our transaction is assigned an ID just like any other transaction, and after our transaction began, the update to Mui's name is committed. Okay, so we know that that's done and that's committed. But shortly after they commit the update, they realize that his name is still misspelled, and they create another transaction to fix it again, and then commit that one as well. So this transaction is given another ID, and you can see here from our series of events that the numbers are increasing here. So now over in TempDB we have two versions, the first original one, the second one, and now in our database, production database, we have the third one here with the current value with finally the correct name for Mui. Next they start a transaction, update Harrison's name, because it was misspelled as well. And our select finishes before Harrison's update commits. So with this series of events, what do you think our select, which is now just finished, started here, step 4, and finished here in step 8, what do you think our select will give back to us? Well, let's see. For Darren, that's pretty straightforward. It hasn't changed, and the current data is the one that's always been there, so we would get Darren's name back. And the way SQL Server is going to do this is by comparing the version that's in the database, in this case 60, with the version of the select, which is in this case 300. It says, okay, this was data that was in place before the select started, therefore that's the data that I'm going to get. For the next row, for Brad Burr, it says, okay, I have information over here. There's some new data, or the old data is over in TempDB. I know that, but I know that that was committed before I had my select. Therefore, it'll pull out, use the new data that's currently sitting in the production database for our query. So we get Darren Bender and Brad Burr. Now, when it gets to Mui, it gets a little more complex because there are two updates for Mui, so there are three IDs we need to compare. SQL Server is going to use two criteria. First, it's going to look for the update that has the largest value that's less than our transaction ID. So the 400 is going to be cast out automatically thrown out automatically because it's greater than 300. And the larger of the two updates to the TempDB database is the 200. However, the second criteria that SQL Server uses is that it has to be from a transaction that was not active when our transaction started. So here in step 4, when our transaction started at 300, the update here was still running. It hadn't been committed yet. So SQL Server took a list of all of the open transactions and remembered each one. So as it got down to this point, it would say, all right, you know what? This transaction 200 was still open. It wasn't finished. Therefore, I can't use this data because I don't know if it was subsequently rolled back or committed. So what it'll do is it'll pick the 70 because 70 is the highest ID that's less than 300 that was not part of a transaction that was open when the select began. All right, the Harrison update isn't committed yet, but the data has already been written to the data file, and the transaction has an exclusive lock on this row at the point that when our select finishes. Typically, that would mean that our query would wait until the transaction completes, either committing or rolling back before it grabs the appropriate data. But since SQL Server knows by looking at the transaction IDs that our transaction started before this one, it also knows that it really doesn't care if the new data is committed or rolled back. The row that was in place and committed when our transaction began is in the version store over here in TempDB. And we can get the data from there without waiting for the lock on the table row to be released. So it will look and it'll say the largest number, largest transaction, or the largest version ID that's less than 300, that's not part of a transaction that was open when we began our select, is 40, and we'll get Harrison Dieback. And this is really the power here of snapshot isolation. The exclusive lock on Harrison's row didn't block our read. We didn't need the shared lock. Because we didn't need a shared lock, our read won't block any writes either. Sounds a lot like no lock, doesn't it? Now this may seem like an incredibly complex bit of logic to figure out, well, what data am I going to get back? But really there's one simple thing that you need to remember, and that's that the select will retrieve all the committed data as of the point in time when the select began. And if you keep that in mind, you can very easily figure out where your data came from and what data you'll get back. Okay, so in summary here on the snapshot isolation, it doesn't take read locks. The data is read from the version store in TempDB or the table, whichever has the data that it needs to get. And this also helps to reduce the bad data issues, and the data is consistent as of a point in time. In order to use snapshot isolation, there are two different commands that we need to know. The first is allow snapshot isolation. The second is read committed snapshot. When we enable allow snapshot isolation, that starts generating row versions. So that's when each row starts to get its own version, and SQL Server starts to store old versions in TempDB. That allows you now to create a transaction that specifies the snapshot isolation level. Now with the snapshot isolation level in a transaction, the version that's used to satisfy the query is the version at the point in time when the first query is executed. So when you write out begin transaction, that doesn't start that's not the point in time that SQL Server uses to satisfy a query. It's when you execute the first query that accesses data after that. At that point, a version is assigned to your transaction, and all of your queries will be consistent as of that point in time. The second command, read committed snapshot on, builds on snapshot isolation. And what it does is it changes the ways that read committed isolation queries run. Instead of taking shared locks for data access, it will use the read committed will use the version store by default. Now, this changes the way that the read committed works. And with read committed snapshot on, the data that's used to satisfy the query is the version of when the data access began, not when the transaction began. This means that if you're inside of a read committed transaction, that non-repeatable reads are still possible. You still may get a read later that is different, has different data from what you had earlier in the transaction. So what the part that changes is that it's by default, instead of taking out shared locks like read committed does, it will now use the version store to satisfy the query. So there's a little bit of a difference between those two. Allow snapshot isolation tends to work a little bit more like serializable, and read committed snapshot on uses the version store, but works more like read committed with a little bit of a flavor of no lock. Okay, as we look at some examples of the different transaction isolation levels, we're going to start with read committed. Read committed is our default, so if we haven't changed our isolation level, that's the isolation level that we'll be using, and that's the one that's definitely the most common. We set our isolation level by using the statement set transaction isolation level, and then then indicating the level that we want to be running under. So I'm going to use this statement here to set my isolation level to be read committed. Then I'm going to begin a transaction and select all the rows and all the columns from my customers table. Okay, so we got 5,125 rows back. I'm going to come over to this window here, which I've called lock check, and here I'm going to run a query that gives me the type, number, and whether or not it's been granted for each lock in the database. So I'm going to restrict it to the two sessions that I'm going to use for the demo here, session 55 and session 51. When I execute that, what I see is that there are only two locks right now for those sessions. Each session has one, and there's a shared lock on the database. I don't see any locks on the rows, the pages, or the tables in the customer database that I executed. The reason is that, as we talked about before, in read committed isolation level, the shared locks are only held for the duration of the statement. If I'd come over to the lock check page faster, while that query was still executing, we'd have seen there had been more locks on either rows, pages, or the table itself, and that those locks would have been freed as soon as the statement had finished. Okay, with this transaction begun, I come over to this second session here, which is a separate session, set it to also be read committed, highlight the whole thing, there we go, and then I can do a select from customers, and it completes as well. That's because shared locks are compatible with each other. Even if I had been able to run both of these queries simultaneously, they still would have executed because they were both reading and neither one of them were doing any data modifications. Now what I'm going to do is come back over to my first window, and I'm going to execute an update. This is going to change the address where the primary key equals 2, which will be this row right here. It's going to change the address to be the word changed. Now when I go back and look at my locks, I can see that there are some locks there now. There is a row lock on the row that I'm changing. There's also intent exclusive locks on the page and the table, the customer's table. This row lock is still there even though the query is finished executing, because exclusive locks are held for the duration of the transaction, regardless of the isolation level that you're in. If I wanted to go look, I could actually go out to navigate to file number 1, page number 114, and look in slot number 1 on that page, and I can see that the row that is locked is indeed the row that I had updated on the previous window. Now with this session here, with my window 1 having an exclusive lock on this row in the customer's table, if I come back to my second session now and I do my select again, I can see that it's waiting here. It's taking a lot longer. In fact, this query here will wait forever. The reason is because it's looking for a shared lock on the row, and it's being blocked by the exclusive lock in the other session. If we go back to our lock check and re-execute, we can see that session 55 has requested a shared lock on the same page as being held by the exclusive lock, but it has not been granted. It is waiting. And it will wait forever until either the first session rolls back or until someone cancels this query. So if I go back to the session that has the lock and I execute a rollback, watch right here, this part of the screen where it says executing. As soon as I roll back, that query executes and finishes. Notice that it has the old data. Because I rolled back, it didn't see the data that had been changed inside of the transaction. Okay, now let's look at the read uncommitted isolation level and see what happens and what's different. If I set my transaction level to read uncommitted, and now I'm going to begin a transaction, and again I'm going to run a select. I'm going to come back over here, do the same thing in my second window, so both my queries are in read uncommitted. Again, they both executed. When I go back to look at the locks, we still only have shared locks on the database, and that's because we didn't get over here fast enough. But if we had actually been able to get over here while those queries are still running, they wouldn't have shown up here because read uncommitted doesn't request shared locks. Now if I do my update, and you can see, because it's still actually just a little bit higher up here, this is exactly the same change. My update succeeds. I come back over here though and run my select, the query executes successfully. When I check my locks, session 51 has the exclusive locks just as it did before, but this time my session 2 didn't request a shared lock. Because it didn't request a shared lock, it wasn't in conflict with the exclusive lock on the row or the intent exclusive lock on the table. So it was able to execute without any conflict. If I look at the data, you can see that the data that it got back was indeed the changed data, which has neither been committed nor rolled back yet. If I come back here and execute a rollback, execute my query again, see the address is back to its original value. I had a dirty read. You could actually see it right there in the window. All right, let's look at repeatable read. First, let's look and see a non-repeatable read. So what I'm going to do now is I am going to come to my second window here, change the isolation level here to read committed, and I'm going to do a select star, and now I'm going to come back over. I'm going to do an update. In the wrong spot. Here we go. I'm going to do a begin tran and do a select for that customer ID number 2. Knew that didn't look right. All right, now I'm going to come back and I'm going to do an update. The update succeeds. So I'm inside of a transaction, and that update succeeded. If I come check my locks, there are no locks here, just the shared locks of the database. The update was not done inside of a transaction, so it got an exclusive lock only for the amount of time that it took to complete the update. My begin tran here, I did a select star inside of the transaction. Or I do my select star again, I can see, we're going to watch the address here. The address has changed, even though I was inside of a transaction. This is a non-repeatable read. I was in a transaction. The first time I executed the query, I got one value for the address. The second time I executed the query, I got a different value for the address. I was not able to repeat my read inside of a transaction. And that's the type of read error that I'll get in read committed. So let me close my transaction out here. I don't need to do anything over here. So what I'm going to do now, though, is I'm going to change my isolation level to be repeatable read. I'm going to do the same work again. I'm going to select star from customers. Now when I go check my locks, I can see that I actually have some intent shared locks on some pages. If I come down here to the very bottom, I have a shared lock on that row that I have read. So now when I come, I want to update that address, my query doesn't return. When I go look at the locks, I can see that for session 51, it has requested an exclusive lock. It's actually requesting a conversion. It already has an update lock on the row. It's trying to convert that update lock to an exclusive lock. This indicates that it was able to read the row because it got an update. And update is compatible with shared. So if you have a shared lock, you can get an update lock. So it was able to get an update lock, but it wasn't able to convert that lock into an exclusive lock yet. And it's waiting, and it will continue to wait until our repeatable read query finishes. So if I come back over here and look, okay, so I got non-repeatable read. That was my update that I had before. If I do a select again, I get non-repeatable read again. The update here to be blocked is not executed. It's being blocked by my repeatable read transaction over here. Now if I go ahead and commit, again here, watch the executing. As soon as I commit, it executes. Now if I run the query again outside the transaction, I can see that it's been updated. But the update was blocked while I was doing my select because I had requested repeatable read. Okay, the next isolation level is serializable. But before we get there, let's look at a phantom read. So now we're going to stay in repeatable read isolation level, and we're going to start a transaction. And here what we're going to do is we're going to select more than one row. We're going to get a range of rows. We're going to get everything that starts with BRE, which is going to give us Brett Jensen. We can see that we have 5 rows here for Brett. Now if I go look at the locks, I can see again a bunch of intent shared locks. I can also see now that I have some shared locks. Actually, it's a little smaller. Let's look at this area here. Some shared locks on some pages and rows in the table. Okay. Now when I come over here, look at a phantom read, I'm going to insert another Brett Another Brett Jensen. And the address I'm going to put in for Brett is 0 phantom. Aha, that one ran. Why did it run? Because I didn't have a lock on this new row that didn't exist. I do my select again. You see that I get an additional row that I didn't have before. Even though I was in a repeatable read transaction, it doesn't prevent new rows from being added in. This is a phantom read. Go ahead and commit that transaction. And now we're going to change the isolation level to be serializable. Now when I begin my transaction here, I get the 6 rows, the phantom read that I had from before, which is no longer a phantom read. This is just a regular read, and the 5 rows that were there before. When I go check my locks this time, I now have a much higher level lock. SQL Server chose to lock the entire table with a shared lock. This is usually we get an intent shared on the table and a shared lock at a lower level. It locked the entire table with a shared lock. And when I go back to my transaction page 1 here, my file 1, and now I'm going to do a different insert. This one's going to be, oh, phantom strikes again. Now this insert's blocked. The reason this one is blocked is because I have a shared lock on the entire table. When I come back and look, I can see that we have an intent exclusive lock on the table that's waiting for the shared lock to be resolved. And it will wait until this transaction either completes or until the query is canceled. I'm going to come and cancel the query this time. So there we can see that our phantom insert was blocked. Now there's an interesting piece here that we can look at with indexes. They look a little bit different. So I'm going to create an index now on first name, which is the field that we were querying on. And you'll begin another transaction that's serializable. I'm going to, again, use the same query. We have the same 6 rows here. Now, though, when I go and look at the logs, I see something new. What I see here are key locks. And here's a resource description, which is a little funky here, but what it's done is it's locking a range on the index for that table. And that allows it to be a little bit more refined. You'll notice that on the object, we just have an intent shared lock instead of a shared lock. We also have shared lock on individual rows. But up here, we have key locks on a range. So if we come back over, we try to insert Brett Jensen, we can see again that it's blocked because those rows are locked. But what if we try to insert something that's outside the range? The query range that we had here is BRE%, which means anything that starts with BRE. If we try to do an insert that starts with ZEP, that's outside the range. And now with the index, SQL Server did a little better refinement on its locking. It actually lets us do that insert. Did that change our phantom reads here? No. If we execute our query again, still inside the transaction, we get the same rows back again. SQL Server was able to lock just the rows that it needed and just the ranges that it needed. So it was still able to allow inserts that were outside that range. Now, if we now do inside of our transaction a select here, where we're also looking for Z, now we'll get the Zephyr. Now if we come back and try to do another insert, starting with Z, now we're blocked here as well, because at this point, the select has become part of the transaction that's serializable. And now we're being blocked by the shared lock held by the serializable transaction. Okay. All right, let's look at our last isolation level, which is read committed snapshot. Now, remember we have 2 statements that turn this on, allow snapshot isolation and read committed snapshot. We're actually going to turn these on. We're going to turn them both on. In order to do that, we have to be out of the database. You see here that it's blocking and it's waiting. So I'm going to come over to my other 2 windows, change them to be using the master database. So there's no one else in AdventureWorks. Oh, they're finished. So now I can change them back so that we're back in the right database. All right. Now what we're going to look at first we're going to look at the read committed transaction now that we have read committed snapshot on. We're going to do our select from customers. Let's do this first. Now we begin this transaction read committed. We're going to do an update. Now that should give us an exclusive lock on that row. So let's come back here and look. Sure enough, we have an exclusive lock on the row. Now when we come back to our second window here and we do a select star, how long will this one wait? If you remember right, under read committed, we have an exclusive lock. It won't do a dirty read. Well, it finished completely. The reason that it finished is it was able to resolve the data that it needed from the version store. Let's come back and look. The address that we were setting for PK2 is changed. We can see that that's not what we got. What we got was blocked. Remember, we changed the address to blocked earlier when we were looking at blocking. So we got the old value because the transaction over in window number 1 hasn't committed yet. But our read over here wasn't blocked because it was able to get the information that it needed out of the version store. So there's a look at the read committed snapshot isolation level. We can go ahead and roll back. Okay, now we're going to talk for just a second about a deadlock. Now you may ask, what is a deadlock? Well, let's imagine a situation like this one. We have an order table. And among other columns that we're not showing here, there is a paid column and an inventory column. The paid column indicates if the order's been paid for, and the inventory column indicates if there's sufficient inventory for this order and it's ready to be picked and shipped. Now imagine we have two transactions running simultaneously on different connections. One is marking orders that are ready for inventory, and one is marking the orders that have been paid for. So our first transaction starts up, and it marks order number 100 paid. So it's going to get a lock on that row, an exclusive lock, and it's going to go ahead and update the data. Now the second transaction marks order 102 that inventory is available for it. So it goes ahead and gets a lock on that row and marks and updates it as well. Now our first transaction, as you can imagine, wants to update order 102 and mark that it's been paid. Since the second transaction already has an exclusive lock on that row, and we're using our default isolation level here of read committed for both transactions, it's going to wait. It can't get an exclusive lock when another row already has an exclusive lock. So it's going to wait until that lock is released. This is called a block. Now we're not to the deadlock yet, but we do now have a block. Remember, blocking's not bad. It's a good thing. It ensures that our data is consistent. How long will our transaction 1 wait? Well, it'll wait forever until somebody cancels their query, or until transaction 2 finishes and either commits or rolls back the change that it made to order 102. At that point, it can go ahead and finish its work. So at this point, now transaction 2 is going to go ahead and try to update the inventory on order number 100. Since transaction 1 has that row locked, it waits. Now you can see we have a much bigger issue. Blocking isn't normally a problem, but in this case it's impossible for either transaction to get what it needs. Transaction 1 can't progress because it needs something transaction 2 has, and transaction 2 can't progress because it needs something transaction 1 has. They are both stuck in a state that can never be resolved, and they'll both sit forever. This is a deadlock. Now, SQL Server will recognize this situation and decree death to one of the transactions, forcing it to roll back and sending an error 1205 back to the client. Once that's happened, that transaction is rolled back, its locks are released, and with the locks now free, transaction 2 can finish its work and commit. Okay, it's important to realize that blocking is different than deadlocking. Deadlocking is a situation where blocking cannot be resolved. Typically, when you see blocking, particularly heavy blocking on SQL Server, it's because there's a connection that has a lot of resources locked and other connections can't get access to what they need. That's a fine thing. When it turns into deadlocking, though, it's something that's very different. SQL Server automatically handles that, and you can actually discover when deadlocks occur by turning on trace flag 1204 or 1222. And when you enable those trace flags, deadlock information is written out to the SQL Server error log. It'll tell you the SPID, the connection information about the connection that were involved in the deadlock from both sides, which one was picked as the victim, and it'll also give you the statement that was executing that caused the deadlock. You can also use SQL Profiler to capture a deadlock graph, but in that case, the profiler actually has to be running at the time the deadlock occurs in order to get the deadlock graph. Now, SQL Server will typically kill the cheapest connection, whichever one it's easiest for SQL Server to roll back. But you can also change the priority of your own transaction to make it more or less likely to be picked as the loser. Now, typically deadlocks are caused by competing modifications, but here in a minute we're going to look at an example of a deadlock that's caused by something else. And typically when you run into the deadlock, the solutions include rewriting code so that the tables and rows are accessed in the same order, or making smaller transactions so that there's less inside each transaction, or adding an index. Adding an index may influence SQL Server to lock fewer rows, or changing the isolation level using something like read committed snapshot, which we talked about earlier, to reduce the amount of contention in the table. Now, on the indexes, sometimes adding an appropriate index will reduce the window of opportunity for deadlock just by making the query run faster, so that it no longer happens. But if that's the case, adding the index will just hide the problem and really isn't a permanent solution. Now, slow code or resource-heavy contention makes the window of opportunity larger for deadlocks. If you have a spot in your code where you are prone and a deadlock might happen, having that section of code take longer to execute makes it more likely that a deadlock will occur. Although they certainly don't help on a heavy system, typically deadlocks are a symptom of the slow system and not necessarily the cause of a slow system. Okay, let's go ahead and take a look at a deadlock in an example. Okay, for our deadlock demo, we're going to use the same customers table that we were using before. And we're going to again have two sessions, and we have our same queries checking for what locks are present. Here in this first session, we're going to use the repeatable read isolation level. And we're going to begin a transaction, and we're going to select out the first 2,000 rows from the customers table. When we execute this, because it's a repeatable read, we'll take out shared locks on the rows and pages that we needed to read this data. And because we're in repeatable read, those locks will continue as long until the transaction is committed. What I'm simulating here is a select query that is either slow or is reading a lot of data or takes a long time to run. Right now it's read through the first 2,000 rows. When we execute this, we'll simulate that it's reading through the rest of the rows. So we're simulating a slow running select query here that's reading from PK1 up through PK2000, and then it'll continue on to the rest of the table. In our second window here, we're going to use the read committed isolation level. Not that it really matters which isolation level we use here, because we're only going to be doing an update, and any one of them would act pretty much the same way. But we're going to use read committed, then we're going to begin a transaction, and then we're going to run an update. Now this update here is going to update all the addresses for records between 3,000 and 4,000. What I'm simulating here is an update that's starting at the end of the table and working forward to the front. Maybe SQL Server decide to split this query up and use parallelism. So each section of query is running on a different processor, and in this case we would assume that, the part that got the 3,000 to 4,000 section finished first before it got to the 1,000 to 3,000. Or maybe SQL Server just decided to do the update from the end to the front. So what we have here now is we have part of the table that's locked in our first session with shared locks, and part of it that's locked in our second session with exclusive locks. If we go check our locks for these sessions, we can see that sure enough, session 1 here has intent exclusive on a bunch of pages and exclusive on a bunch of rows. As we get down here to the bottom, we can see that session 53 has intent shared on some pages and shared locks on some rows. But right now there hasn't been a conflict because they're locking different parts of the table, and that's all fine. Now what we're going to do is we're going to come back to our first session and we're going to say, okay, the select that's gotten this far, let's assume that it keeps on going and it finishes. And again, we're kind of simulating a single select here. You can see that part of it completed. In fact, we got rows all the way down to, we look here, PK 2994. At that point, it kind of stopped. You can see it's still running, but it's hung. The reason it stopped here is because at this point it got to the page where there are some exclusive locks there and it can't convert the lock. It's waiting to get a lock on that row 3000. But that row 3000 has an exclusive lock on it, and so it's waiting. It's waiting for this one to finish. And right now it's running fine. It just assumes that eventually this transaction will commit or roll back. Either way is fine, and then it'll be able to continue its select. If we went over to our lock check, and we're not going to, but if we went over there, we could actually see the row that this query was attempting to execute. Actually, let's go look, because this is actually kind of interesting. If we look, we can see the row that it's waiting for here is on page 1, or excuse me, file 1, page 335, and slot 9 is the one that it's waiting for. Let's see if we can get lucky here. 335 and 9. 335 and 9. You can see that that session 51 has an exclusive lock on that page and slot. If we went and looked this up, and I did a few minutes ago as I was getting ready for the demo, you can see that this slot 9 is actually going to be the slot that row 3000 happens to be in. All right, so we're waiting on this transaction. Session 1's waiting for this session 2 transaction to finish. What happens now if we try to update some of the addresses for rows between 1000 and 3000? Well, at this point, we would be trying to update rows that session 1 has shared locks on. Because it has shared locks on it, it can't return those until it gets its shared lock on the rows that session 2 has. This one won't be able to finish until it gets an exclusive lock on the rows that session 1 has. So we'll have created a deadlock. So I'm going to run this. I want you to watch right up here the executing again, see what happens. As soon as I execute this, it executes successfully. But this query over here is no longer running. It looks like they both succeeded. But if we go back and look, we can actually see that we got the error 1205 here. Process ID 53, which is us, was deadlocked on lock resources with another process and has been chosen as the deadlock victim. Rerun the transaction. So SQL Server had to pick. It detected a deadlock between these two sessions, and it had to pick. And it picked the select as being the easiest one to roll back. So our transaction was killed. In fact, if we try to do a commit right now, we'll see that our transaction is gone. Our transaction's rolled back. We can't commit it because it's gone. The transaction over here is continuing. It's still open. It hasn't completed yet, but it was able to get the resources that it needed to lock the rows between 1000 and 3000. Now we can roll back and close this transaction out as well. If you have any questions about isolation levels that I haven't covered here, feel free to drop by my desk and we'll chat about it. Or you can also send me an email or send me a note on Twitter at EBAChat.